All right, I guess we'll go ahead and get started then. So we're happy to have Silviu and Pufu visiting us from Princeton. We'll talk about accidental symmetries and the conformal bootstrap.
Hello, thanks a lot for the invitation. I'll talk about a short little paper that I wrote this past summer with a bunch of people from Princeton, Shai Chester, Simone Giambi, Luca Iliescu, Igor Plebanov, and Ron Jacobi. And it is related to the conformal bootstrap. So I thought at the beginning I would sort of introduce the topic. So the conformal bootstrap philosophy is to use the symmetry, and by symmetry in this case people mean conformal or superconformal symmetry, as well as flavor symmetry, to constrain the space of conformal field theories or superconformal field theories. And in particular, what are the things that are being constrained? It's the CFD data, or in parentheses around the S, not around the CFD. So the CFD data or the SCFD data, which consists of the operator spectrum. So this is just a list in a CFD or in an SCFD. We can just list all the local operators and their quantum numbers, meaning the spin, their scaling dimensions, and flavor representations. And the OBE coefficients. So the idea of the conformal bootstrap is to think about the space of conformal field theories or superconformal field theories abstractly, and think of a CFD as defined by the operator spectrum of the operators with their quantum numbers and the OBE coefficients, and see under what conditions the CFD data is, SCFD data, I forgot the word data. Under what conditions the CFD data is consistent. And what's exciting about it is that some of the results are quite constrained. Many of these results are numerical, so this problem was can be implemented numerically. I'll say something about it a little later. So if one also uses the assumption of unitarity, assume unitarity, and then the question is, okay, what can one actually get? Well, one can get rigorous bounds on various quantities. For instance, a scaling dimension or an OBE coefficient. I'll just say that, for instance, we get that C is bigger than some number C star. And then what people noticed after obtaining some bounds is that some known conformal field theories almost saturate these bounds. Saturation of bounds. And then if we know a CFD that saturates these bounds, then we can actually turn this into a precision study. of the CFT. So the bounds imply, first get some bounds. If then you know some CFT that it seems like it's almost saturating those bounds, then you can just turn it into a precision studies. It just goes this way.
So the first one is numerical, but then you know,
The
or
first,
do you not know either of them?
the first one is numerical, and then,
So you know CFTs that almost saturate, so you know the CFTs, you know the...
yeah, but in some examples, for instance, the 3D icing model, there are numerical simulations where, and you know the critical exponents that way, and then you can check to see where your critical exponents are in your plots, and if they almost saturate if they saturate the bounds, then you can try to compute other critical exponents from your numerical results. So I think this is sort of the idea of what's been done. Okay. In this talk, I won't do this. I'll essentially stop at the first bullet point here. So what I'll do is to use numerical Bootstrap to rule out the existence of a putative CFT where no other known methods rule it out. Okay? So I will show you an explicit example of a conjecture conformal field theory that just doesn't exist. Okay? So just to help you focus on some of the important things, I want to point out two things. So the first thing that I would need to do in order to argue for such a thing is, well, I first have to define the CFT, and then I would need to calculate exactly a quantity C in the putative CFT. And it must be such that if this quantity C takes any other value than the one that I calculated, then the CFT doesn't make any sense. Okay, so I have to have a clean way of computing something in it, and then I need to show, using the Bootstrap, that the quantity in my putative CFT is strictly less than C star, assuming that my numerical bounds would show that C is bigger than C star. Okay? So, since I'm going to have to do some exact computation of some quantity, supersymmetry probably helps. So then I'll focus on a setup that has supersymmetry.
Why do you know it exactly?
Just to prove conclusively that the CFT doesn't, I just need to show that this C is smaller than some C star. Okay.
Put an upper bound on it. Right.
I guess that would also work if I could put an upper bound, but I would need to be sure of my upper bound.
Okay. This
Okay.
way you don't have to
But in
follow.
the example that I'll show, I can actually calculate it. Okay. So I have a concrete setup which is in 3 dimensions. I'm going to do n equal to supersymmetry, meaning 4 Poincare supercharges. And I'm going to use only chiral multiplets. And I'm going to have a chiral multiplet that I'll call X. And I'm going to have n other chiral multiplets, so I'll call z sub I, where I goes from 1 to n. And I'll just consider a Wezumino model. So this is sort of like one of the simplest conformal field theories that you might want to construct. And so I have these chiral multiplets interacting with just a superpotential interaction, which is this. So I'm going to have an interaction that looks like x times the sum of the zi squared plus some other coupling constant here times x cubed. So some coupling constant times x times zi squared plus some other coupling constant times x cubed. Okay. So this is a superpotential that preserves ON symmetry. And you could just think of this theory as some sort of generalization of the ON vector model to theories with unequal supersymmetry. And so you can think of this superpotential interaction as generating an RG flow from a free theory in the UV, perhaps to a CFT in the infrared. So this is an RG flow that preserves an ON times Z3 flavor symmetry. Okay? Under the ON, X is a singlet, and Zi is fundamental vector. And under Z3, all the fields get multiplied by e to the 2 pi I over 3. Okay. So this is an RG flow that preserves the symmetry. Okay? So I can just try to write down the claims about this theory. And so this is what I'll try to show. The first one is that if n is bigger than 2, the IR CFT can't have only ON times Z3 flavor symmetry. I guess this claim is a little surprising. Usually when we write down a theory that has certain symmetries, we expect that, usually when people write down these models, they expect that there's no symmetry enhancement in the infrared. Unless something goes wrong. So, I mean, you could try to compute some scaling dimensions of operators, and if those violate the mutarity bound, for instance, then you might conclude that, okay, maybe there's symmetry enhancement. But in this case, you can actually calculate scaling dimensions of operators, and nothing goes wrong.
Are those GIs dimension 4?
Yes, they are dimension 4. Yeah, so you can calculate scaling dimensions of operators and nothing goes wrong. So it's a little surprising that I'm saying that if n is bigger than 2, there's symmetry in this theory can't just have only ON times Z3 symmetry. So it's surprising because there are no other inconsistencies other than the one that I'll show. Okay. And this is so that's the first claim. And the second claim is okay, but if there's no IRCFT with the same symmetries as the RG flow, then what happens in this model? Okay? And what happens is that we expect symmetry enhancement for accidental symmetries to On times U1. So instead of On times Z3, we're going to have On times U1. Concretely, in terms of that superpotential, G2 flows to 0. And then the theory, it would be described by G1 over 2x sum of Zi squared, I going from 1 to n. And this theory has an On times U1 flavor symmetry. The On is as before, but under the U1, x has charge -2 and Zi has charge 1. That's a symmetry of the superpotential. If I erase this term, then there's a flavor symmetry under which I multiply x by e to the 2I alpha and multiply Zi by e to the minus I alpha.
Maybe you said it, I missed it. Is it obvious? Why is it obvious that this theory has an interacting fixed point ion?
Well, usually when people write down these models, they assume it does.
Okay.
I guess it's not.
Logically, it could have flown to the trivial theory for some reason.
Yeah, I suppose. But it's yeah. People usually assume it does. Like for the On vector model, you can write it in a similar way. It's just free fields from some quartic interaction for the scalars, and you assume that it has a CFT. Yeah, that it flows to a CFT. Interacting CFT.
How does the U1 anomaly, does it satisfy the kickoff the anomaly condition?
Sorry?
How does the anomaly of the U1, of the new U1 symmetry?
There are no anomalies because we're in 3 dimensions.
Oh, yeah.
So, you can just first, I can just give you some sort of intuition for this. This theory is defined in 3 dimensions, but we can continue it in space-time dimension, and we can study it in 4 minus epsilon dimensions. In 4 dimensions, in exactly 4 dimensions, Wezumino models are not conformal. We need to have gauge fields in order to make n equal 1 supersymmetric conformal materials. So integration from d equal 4 minus epsilon. In this case, we can study this RG flow perturbatively because the theory is almost free. And we can even write down beta functions for these couplings. And for instance, I'll just write down a beta function for G1 as G1 times minus epsilon over 2 plus n plus 4 G1 squared plus G2 squared divided by 32 pi squared, and so on. And you can have a similar formula for beta 2 minus epsilon over 2. Okay. You can just write down what the beta functions are. And then you can try to see what the RG flow lines look like. Okay. And I'll first do it for n equal 1. We just have only one of these Z chiral multiplets. The RG flow diagram looks like this. Here we have G1, here we have G2. And there are 4 fixed points. There's one here, there's one at the origin, there's one here, and one somewhere here. And the flow lines look like this. The one at the origin is repulsive in both directions. This one's attractive in one direction, that one's attractive, but they both have a repulsive direction from which you flow to the one over here. This is what it looks like. So what are these 4 fixed points? the one in the origin is where x, it's just a free theory. X and Z are free. So there, G1 and G2 are both 0. The one over here, G1 is 0, but G2 is non-zero. So we just erase this term. And this theory with just an x-cube superpotential called super Ising model. So this is super Ising times the theory of CI, where the CI are free. There's another fixed point over here, which is the one with G2 being 0. So this here is the theory with the superpotential x sum of Zi squared that I mentioned before. And this is an interacting, in this case, super conformal theory. Okay? So this is what the RG flow lines could look like for all n, but they don't. So for n bigger than 2, they look like this. There are only 3 fixed points, one the origin, one the x-axis, and one the y-axis. And the flow lines look like this. Okay? There's just no fixed point with non-zero G1 and G2.
This is still on the epsilon expansion?
Yeah, these pictures are the epsilon expansion, because otherwise I can't draw RG flow diagrams. Okay? So in this case, you see, so this is again G1, and this is G2. So if I start with some non-zero G1 and G2, what's going to happen is that G2 is just going to float to 0, and G1 is going to be non-zero, and we're going to be at this interacting fixed point where the global symmetry is On times U1. Okay? But this is what happens in the 4 minus epsilon dimensions. It'd be a little hard to argue just based on this that the same would be true in 3 dimensions. Yes?
Isn't the intuition for relevant operators usually that the coupling should increase?
Yes.
Seems like it's not necessarily happening.
Well, unless there are accidental symmetries where, for some reason, the coupling just happens to go to 0.
Okay.
I think you're saying it's just a.
Yeah, that statement
True
is
around
about
0.
in the neighborhood of the origin,
Okay.
but not away from there. Yeah, okay. So then what I want to do is to show you an argument, a proof, that for n bigger than 2, I can't prove it for n equal to, there's no fixed point with G1, both G1 and G2 non-zero in 3 dimensions. And the proof is by contradiction. Assume there is such a thing. Assume there is a fixed point with both G1 and G2 non-zero. And then calculate some quantity C putative. And I'll show you exactly how using F maximization plus supersymmetric localization. And B, have a bound on this quantity C. So show that C putative is smaller than C star. Okay, so for the first part, can try to explain how to do that using F maximization. Maybe I can just split this board more efficiently. So F maximization so the setup is as follows. And this is in general, not necessarily as applied to this problem. So we have a free theory in the UV with some relevant interactions, and that generates an RG flow to an n equal 2 superconformal field theory. So this is an assumption that this happens. And the RG flow preserves Poincare supersymmetry times some flavor group G. Okay, suppose we have such a situation. And suppose the theory flows to an n equal 2 superconformal field theory. The symmetry group of the n equal 2 superconformal field theory is always B24 times some flavor symmetry group, which I'll call GIR. Okay? This is because it's a superconformal field theory. But this always B24 includes the conformal group times U1 R symmetry as the bosonic generators, and then they're also the fermionic generators. Okay? And this U1R symmetry is actually very important because it determines the unitarity bounds, and also there are protected multiplets. It determines the scaling dimensions of the protected multiplets. In 3 dimensions, the scaling dimension is equal to the R charge. Okay? And then the question that F maximization is answering is the obvious question that you can ask. So I should say that this assumes no symmetry enhancement. So then the most obvious question that you can ask is, how is this U1R embedded in G? So this is the question, how is U1R embedded in G? And the answer is a procedure for determining how U1R is embedded in G. And it goes as follows. The steps are: assume some embedding. The second step is, using that embedding, construct an action on the 3 sphere. The 3 sphere is conformally equivalent to the flat space that preserves OSB22 times SU2. This OSB22 has as the bosonic subgroup an SU2 times U1 R. So here the idea is that we construct an action for a theory on S3 that preserves SU2 times SU2. SU2 times SU2 is the rotation group on S3, as well as some U1R symmetry. Okay, and for every choice of such an U1R symmetry, the action is unique. So I can actually write it down. Okay, then calculate f, which is minus the logarithm of the partition function for this theory. And one can actually calculate it using supersymmetric localization. One can actually get quite explicit formulas for this. And then the last step is maximize over all possible choices of the U1R embedding into G. And the choice that maximizes F, maximize F. The choice that maximizes F is the right one. That corresponds to the superconformal field theory. Yes?
When you say it's unique for a given choice of embedding,
Yes.
you mean also for the given free theory that you're starting with? I mean, for the field content.
Yeah. For the field content of this, I'm starting with some free theory and some with some superpotential interactions and preserving that. This action on S3 is unique.
Yes, in information, we have the A maximization to determine the combination of the U1 symmetries and the others.
Yeah, that would be it's the analog of that in 4. So this is in 3 dimensions. The A maximization is in 4 dimensions, and this is just the analog of A
So
maximization.
another.
Okay. So. So, for instance, as an example, when we have only chiral multiplets, phi I, with R charge Ri, and then F from supersymmetric localization is just minus the sum of some function L evaluated at 1 minus I, where the function L is defined by L prime of Z is minus pi Z cotangent of pi Z, and L of 0 is equal to 0. So this that differential equation uniquely specifies this function F, and this is what F is for those choices of R charges. And then we consider all possible choices of R charges consistent with the fact that the superpotential should have R charge 2, and the one that maximizes F is the one corresponding to the superconformal field theory. Okay. So I'm going to apply it in the situation that I was talking about at the beginning, and then show you how we can compute other quantities from just this, just this function f. Okay?
This totally fixes the rich equal to superconformal theory.
Yeah, because it fixes, if I maximize over the R charge, it just fixes the R
Well,
charge.
it fixes the U1 embedding in G, but that's enough to fix the entire thing.
Yeah, and then the symmetry just gets enhanced to OSP 2.4. One can argue that that's true in this case.
Where does that second SU2 comes from? You're constructing an OSP 2/2.
This?
Yeah.
So if I put this theory on S3, the global symmetry is SO4, which is SU2 times SU2. One SU2, the other SU2. Okay. So in this situation, let's just denote by y plus minus z1 plus minus iz2. And the superpotential in this case becomes xy plus y minus plus the sum of x zi squared from I from 3 to n, and then plus x cubed. And I didn't write couplings. I can just say that the R charge of, I can consider some trial R charges, okay? And let's say the R charge of y plus, I'll just call it RZ plus little y. The R charge of y minus is RZ minus little y. The R charge of the other zi's is, I just call it RZ from I from 3 to n. And the R charge of x, is 2 minus 2RZ. So this would be a consistent choice of R charges if I didn't have this x cubed. But with the x cubed, I need to take the R charge of x to be 2/3 because the R charge of superpotential needs to be 2. Okay? So this is just some screwy choice of trial R charges. I just introduced some fake parameter here, y, that should have been set to 0 because all these fields, all the y's and the z's all have R charge. It should have the same R charge if I'm obeying ON if the theory has ON symmetry. Okay? But because I introduced this parameter y, I'll actually be able to compute something else that's not trivial. Okay? So I should say, if we wanted to study the theory without this x cubed, I can just forget about this condition that Rx is 2/3, and then all the other ones would be good enough. Would be good enough trial alternatives. So in this case, f is minus L at 1 minus RZ plus y from y plus minus L 1 minus RZ minus y from y minus n minus 2 L of 1 minus RZ minus L of 2 minus 2 RZ. Okay? And I can set the RZ to 2/3. Yeah, if I set Rx to 2/3, then RZ will also be 2/3. If there's this term x cubed. Okay? So, okay, and the prescription for F maximization is just maximize over all the set of all trial alternatives. So let's just set RZ to 2/3, or Rx to 2/3. And pretty clearly, this function has an extreme when y equals 0 because it's symmetric, or at y equals 0. This term is has plus y, this term has minus y. So df by dy when y equals 0 is equal to 0. And one can compute the second derivative and see that this function is maximized. And so in this case, it's a rather trivial F maximization. I just have one parameter y, and it's maximized when y equals 0. Okay? But the whole function f of y actually carries more information, and actually the second derivative at y equals 0 is very important, because if we multiply it by minus 1 over pi squared, this is what people usually call Cj. It's like a central charge for the ON current, and I can show you where it appears. So the theory has ON global symmetry, and an ON current, conserved current, J, Ij, mu. And the 2-point function of this current, let me write it with braces. Its form is fixed by conformal invariance up to normalization, which is exactly the CJON. Times delta IK, delta JL minus delta IL, delta JK, times eta mu minus 2x mu over x squared, times 1 over x to the 4th. So, this is the 2-point function of the conserved current. It's fixed in a conformal field theory up to normalization. And this normalization constant, Cj, can be obtained from taking the second derivative of f with respect to this parameter y. Okay? And this was explained very nicely in a paper by Cyber, Komargatsky, and a few other people, I forget now. What was that?
Use Ig as the ON index.
What's that?
And for me, use Ig as the ON index.
Yes, I and J are the ON. So you can think of J as having two ON fundamental indices. It's anti-symmetric in I and J. And mu and mu are space-time indices. So these are ON fundamental indices. Vector indices. Okay. So So now we have a concrete. You see, and this was this whole construction assumed assumed no symmetry enhancement. So this is exactly the situation that we want to be in. So therefore, the putative CFT, SCFT, has the following properties: has ON times Z3 flavor symmetry. It has CJON equal to, well, if you actually plug in the numbers in this case, you're going to get 8/9 minus 2/5 square root of 3, which is about 0.521. So this is a normalization in which free chirals have CJON equal to 1. Okay? And we know that the R charges of the Zi are the same as the R charge of X, is 2/3. So, if in this setup we have an IR fixed point with no symmetry enhancement, it must have these properties. And then one can use the conformal bootstrap to actually show that for n bigger than 3, this is inconsistent. So with the bootstrap, show this is inconsistent. The theory must do something else. And briefly, how that works is to study the 4-point function of the ON fundamental, Zi, Z bar J, Zk, Z bar L. And I'll write it again. And when writing down this 4-point function, we can take the OPE of the first 2 operators and the OPE of the last 2 operators. And we should get the same answer as when we take the OPE of the second and third and the first and fourth. Okay. In this consistency condition, after taking the OPE, comes down to 9 equations. So this implies 9 equations. The details are very messy, so I'm just not going to write them. But they roughly take the form of a sum over superconformal primaries. And there are some functions of U and V. U and V are the conformal cross ratios. This is x1 minus x2 squared, x3 minus x4 squared, over x1 minus x3 squared, x2 minus x4 squared. And V is the same with 2 and 3 switched. And this is evaluated x1, x2, x3, x4. And so it's a sum of various functions. The sum should be 0, and the coefficients are just OB coefficients squared, because here I just took the OB twice. So this would be OB coefficients squared. And these functions depend on the scaling dimension, the spin of these superconformal primaries, as well as their charges under the flavor symmetry. So they depend on the ON representation and on their charge. Okay, so let me just explain this. So this is, let me write it here as well. So here R is ON representation. It can be either singlet, anti-symmetric, or symmetric traceless. It's the ON representations that appear in the product of two fundamentals. And C can be 0 or plus minus 2. It's the charge under this, well, we can just multiply Z by a phase. And so if the ON fundamental has charge 1, then this would have and X by the same phase. C is proportional to the U1R charge of the field. Okay, so here we have, but here I just have Z's. So these Z's have equal R charge, and in the OPE of Z with Z bar, for instance, we only have objects of 0 R charge, but in the OPE of Z with Z, we could also take, we have objects of twice the R charge of Z, so this is what the C is doing. Anyway, the equations are pretty complicated. But then, very briefly, how does obtaining a bound on Cj work? How is Cj even related to this? So it's customary to take the OP coefficient of the identity operator, which is one of the operators that appears here, to be 1. So lambda, the identity operator has dimension 0 and spin 0, and it's a singlet under ON, and it also has charge 0, U1R charge 0. So take this to be 1 as a normalization condition, and then one can show that lambda 1, 0, A 0 squared is 2 divided by Cj ON. This 2 is probably not very important because I didn't tell you what these functions were. Obviously, if I multiply them by something, then I would have to divide this lambda by something. So here, this is an operator of dimension 1 and spin 0. This is the superconformal primary of the ON conserved current multiplets. Okay?
How do you normalize the current J?
You normalize it canonically such that when you take the OB between J and some fundamental field Z, you get Z grid with no other coefficient. Okay? And okay. And then we can just write the crossing equation, this equation over here, by separating out the identity contribution and the contribution from the conserved current multiplet. 2 over Cj ON times F10 A0 UV plus sum of all the other ones, lambda squared F equals 0. And then the idea, and this is what's done numerically, to find a linear functional alpha such that alpha of F is positive for all these guys, but not necessarily for the first two. And if we do that, we can apply this linear functional to the whole equation. And and also that alpha on F10 A0 of UV is equal to 1. This is just a normalization condition for the functional. And then if we apply the functional to this equation, we find that 2 over CJON is less than alpha minus alpha acting on F00. Okay, so if you can find a functional that's positive on all of these functions that I didn't write down, and it's also equal to 1 and when acting on this other function, then you have a bound on CJON.
What is the range of delta you're assuming?
So these are all the, right, that's a little complicated. It's just, the deltas are satisfied unitarity bound. So for all the operators, I know what representations can appear in these OPs. And I'm just asking that alpha be positive on the F's corresponding to those representations. I'm not assuming anything other than unitarity bounds. Okay, so this is a lower bound. This is an upper bound on 1 over Cj, so it's also a lower bound on Cj. And I can just plot it. So if you see what happens, the plot looks like this. So this is CJ1. And this is a function of the archer. And this is the value 2/3. Of course, in order to exclude this theory, you only need to do this for the archer of z equal to 2/3. But I'll just show you what the plot looks in general. So let's just say that this is 1/2. This is the free theory value. And the plot looks like this. So here we have this 0.512, and here we have 1. So the theory would be here. So this is where the putative SCFT is. And the bounds look sort of like this. So this is n equal 3. N equal 4 looks exactly the same up to here when it does. So it does something more like this. So this would be n equal 4. And for instance, if you were to plot larger values, n equal 9 would look like this. N equal 12 would look like this. So they all agree in the region close to 1/2, but then they go up. So this is a lower bound on this quantity. So this is excluded, this region here. And it's allowed above. So this putative CFT is just excluded. Right? You can try to ask, and where are the theory that's not excluded? My claim is that this theory with x zi squared is the actual IR fixed point. So you can ask, okay, where is this one on this plot? Where are these theories on this plot? And you can compute CJON for them in exactly the same way. You just don't plug in RZ as 2/3. You maximize over RZ. And they're exactly here, 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 and so on. So these are these theories here, and they all accumulate on this line. So these are the theories corresponding to zi squared. So they have ON times U1 local symmetry. Okay. So maybe I can just write some conclusions since it's getting late. So the putative SCFT with no symmetry enhancement is excluded if n is bigger than 2. There is some evidence for symmetry enhancement to ON times U1. and this comes from the 4 minus epsilon expansion, I have no other way of showing that this is actually what happens in these theories. And I should say again that this is a little surprising because if you assume that there's no symmetry enhancement, you don't run into any other contradictions. So I'd like to draw a more general lesson. And that one should check the consistency of proposed SCFTs with Bootstrap, because there are examples like this one where nothing goes wrong, yet the theory, if you assume no symmetry enhancement, does violate unitarity in a more subtle way, and you'll be able to see that more subtle way using the Bootstrap, but through no other methods that I know of. Okay, thank you.
Questions? Daniel?
What happens for n equals 2 on your plot?
For n equals 2, this analysis cannot distinguish between the theory that has, well, another way of saying it, the CJON is the same for the theory that has ON times U1 symmetry and the theory that would have only ON times Z3. Because CJON in this calculation really just depends on the R charges of the field, but when n equal 2, the R charges are 2/3 even for this theory. I guess in this theory, when n equal 2 is also called the XYZ model. And the R charges the free fields. So you can just write down, I guess, okay, maybe I shouldn't write down the change of variables right now. But you can write down you can redefine Z1 and Z2 by taking linear combinations of them, such that the superpotential looks like X times Y times Z.
Ah, very good. Okay.
And then there's a permutation symmetry, and you see that the R charges of all these fields are 2/3.
So it's still true that the symmetry enhancement is not in respect.
It's still true. In the 4 minus epsilon expansion, that's certainly true.
Yeah.
That does happen.
But for n equals 1,
Oh, and for n equal 1, there exists for sure a fixed point that where both G1 and G2 are non-zero.
Yeah.
You can see that clearly in the epsilon expansion.
right?
And also there, if you do some redefinition of these fields, you can see that that's really two non-interacting copies of the superizing theory.
Very good.
So you know that must
That's
exist.
great.
Good questions, yeah.
So for symmetry enhanced case, for example, the symmetry ON cross U1,
Yes.
are these SFTs looked just at the boundary of the Bootstrap result?
Yeah, it is. There's some sort of
Saturation.
kinks that become sharper and sharper the larger band, at large end, and yeah, it's very close to saturating these bounds.
So could you also limit in the beginning so you can start the process in safety at this point?
Yeah, you can study more other properties of this theory. We are trying to do that.
You imagine the kinks would get sharper for finite n if you were looking at, say, more four-dimensional?
Probably, I would hope so. We're imposing more gaps in the spectrum. I mean, this would really
So the text is also-
yeah, that's right. Yes.
Is there any higher spin theory that is due to the larger of this guy?
Yes. You can take, you can have in M theory, you can consider, maybe not to the large n limit, but to the n equal 5 case. So you can consider the Calabi-Yau cone, which is sum of zi squared is equal to 0, I equal 1 to 5. And then you can consider putting M2 branes at the tip of this Calabi-Yau cone. And if you just put one M2 brane, that's described, that is described by this. There's some papers about this.
Okay. Let's thank you, Silviu.
So, what goes wrong with maximization of various?
Why do you insist?
Yeah, you don't have access to that symmetry. So F maximization just says that the U1R symmetry mixes with various global symmetries. But in this way of calculating it, you don't have access to the accidental symmetries in the IR. You can't compute F on your free sphere in an unconformal situation. The symmetry only happens in the conformal fixed point. You don't have access to it. You can't mix with it. You can imagine perhaps there's another description where you would have access to it. And that's indeed true, that you just erase the exclude term, and then you do have access to it, and then you can compute.
Pick up Benny, the bigger symmetry.
Yeah. Right. You just have to consider a different RG trajectory where you have symmetry.
Can you remind me what's the status of
Yeah, I believe that's proven. I mean, Jeffries' original paper came very close to it. And I think, I mean, the only thing that Jeffries didn't was that, well, he proved that F is extremized. He didn't prove that it's maximized. Right. So then you just have to study very carefully the second derivative.
But that's just the unitarity of your model.
Yeah. So what these people did, they just related the second derivative of F with respect to this trial parameter to some coefficient that appears in the 2-point function of some conserved current, which needs to be positive by unitarity. So that's exactly what I used.
Here you chose these with your the kind of the super control primaries on the
Mm-hmm.
That's because supersymmetry
Relates.
that be down there, right?
Yes. Yes.
So in principle,
Supersymmetry and yeah.
in principle, you could still use that one. Using the, let's say you don't consider the B on delta equal to 1, L equal to 0. You could still use directly the current.
Yeah, I could use directly the current. That's correct.
Nice.
That's correct. Yeah, and these way of yeah, I guess it's customary to only sum over the superconformal primary, but I could just summed over multiplets and considered any operator. I just need a representative of that multiplet. So all the coefficients of the operators in the same multiplet.